Hi guys, today's lesson is on 4.3 trigonometric ratios. So what we're going to do is use the unit circle to write trig ratios or trigonometric ratios. And what we need to know is good old SOHCAHTOA to do this. So back in grade 10, we learned about SOHCAHTOA. Basically what it's telling you in the SO is that sine of any angle is opposite over hypotenuse. Cosine is going to be adjacent over hypotenuse. And tan theta is opposite over adjacent. Now, those are actually what we call the primary trigonometric ratios because they each have a companion to them as well. So their companions are called cosecant, secant, and cotangent. Now, what these companion ratios are is they're basically the original one. So if I look at sine, opposite over hypotenuse, but flipped. So cosecant matches with sine, and it's going to be hypotenuse over opposite. So you can see that that fraction just got flipped. Same thing with secant. Secant matches with cosine, so it's going to be hypotenuse over adjacent. And cotangent matches with tangent, and it's going to be adjacent over opposite. So these are the reciprocal trig functions, basically those fractions getting flipped. Another way that we can think about this is it's 1 over its companion. So if cosecant is a companion to sine, it's going to be 1 over sine. If I subbed in for sine opposite over hypotenuse, the 1 over makes me flip that, and I end up with this. Secant is 1 over its companion, which is cosine, and likewise for cotangent, 1 over tangent. So let's just write these out. These are the spellings if you're interested. So I've got the abbreviations that show up on some calculators. Most of them just have the primary trigonometric ratios. But what I'm actually saying when I write CSC is cosecant. These are on your formula sheet, and this is exactly what you're given. So you're given cosecant, secant, and cotangent all as 1 over the primary trigonometric ratio. But you can also remember that this just means if sine is opposite over hypotenuse, that cosecant is the flip of that, the reciprocal of that, or hypotenuse over opposite. Secant would be hype over adjacent, and cotangent would be adjacent over opposite. So really, with a very small section on the formula sheet, you have a lot of really useful information. One other thing I'd like to review before we move on here is I'd like to review something called the cast rule. I once had a very hilarious student who got this whole section on his 20-1 exam wrong because he remembered cats as in meow instead of cast. So make sure that you spell it right. And what this rule tells us is which primary trig ratios are positive in which quadrant. So remember when we talk primary trig ratios, that's good old SOHCAHTOA that you've been learning since grade 10. So sine, cosine, and tangent. I want you to draw a Cartesian plane. First thing that we know, since we've been using this all year, is the quadrants. 1, 2, 3, 4. I usually suggest students write this at the top of their formula sheet so that they memorize it. And it basically, the way you write the quadrants is like a big capital C. I start in quadrant 1, and if I were to draw a big capital C around the outside of the Cartesian plane, I would map out quadrants 2, 3, and 4 as I go. Now, CAST does not follow the quadrants. You actually start in quadrant 4 with your C. You still go counterclockwise, and you spell CAST. Now, it's a shortened version of what you need to remember. What it's telling you is which primary trig ratio is positive in that quadrant. So what does this stand for? Quadrant 1 stands for all trig ratios positive. So like we saw in the unit circle, our cosine and sine ratios are positive. And since tangent is just sine divided by cos, if I take two positive numbers and I divide them, I would get a positive. This quadrant 2 is telling us that it's your sine ratios, remember, that are positive. The CAST rule is always telling us what's positive. And by consequence, we can actually decide what's negative. If sine is the only trig ratio that's positive, that would mean that cosine and tangent have to be negative. Now that we know companion trig ratios exist, we can expand this to say sine is positive, as well as sine's companion, which is cosecant, and everything else is negative. Now, I don't like to write another C on here because does C stand for cosine or cosecant? That can be very confusing. I just leave it as CAST, and it represents only primary trig ratios. Then you use logic in your formula sheet to figure out what would be known about the companion trig ratios. T stands for tan positive, and C is cos positive. Remember, all other ratios, primary trig ratios, would then be negative. Let's do this first example where we want to determine the 6 trig ratios for the point P at 3, 4 on the terminal arm of an angle in standard position. All right, what this all means, an angle in standard position means that on your Cartesian plane, and I'm only going to draw the first quadrant here, because I know my point is positive. What quadrant do I have positive x and y values in? Just quadrant 1. Standard position means your terminal arm, or this thing, comes out of the origin. It's not coming out of anywhere else on the Cartesian plane. This terminal arm has this point P on it at 3, 4. Like we saw when we derived the unit circle, a point in this quadrant that's on this terminal arm would be obtained by going 3 in the x direction and 4 in the y direction. If I trace those out, I've made a right angle triangle. And we know that all of SOHCAHTOA applies to right angle triangles. Now this is quadrant 1, so my reference angle and my angle in standard position are the same thing. Now I need to have all 3 sides of the triangle in order to label, or in order to state all of my trig ratios. So the first step is to find the hypotenuse of the triangle. We've been doing this for so long now, it should be pretty automatic that that hypotenuse is obtained by going a squared plus b squared equals c squared. And I'm just going to jump to the second step of square rooting that. So we've got 9 plus 16 is 25, and if I square root that, I get 5. Nice and simple example with a whole number there. We'll do some more complex examples in a minute with radicals, which are more common, but here's some nice whole numbers to start us off. All right, what we're showing so far, all of this work that I've written down is determining. When we say determine in math, it doesn't mean write an answer down. It means show all of your work. So you need to have a picture to accompany your work in all of these questions. Now I'm going to write my trig ratios really methodically so that I can do this easily. I'm going to start with sine, cosine, and tangent. And then next to them, I'm going to put their companions. When I do this really methodically, it means that once I have the answer for sine, I literally just have to flip it to get my answer for cosecant. So I'm going to write cosecant, secant, and cotangent right beside their companion trig ratios. Now, just keep in mind your little memorization technique that you'll want to use is the companion to sine is not secant. It's not that the letters match, it's that the letters are opposite. So sine and cosecant match, so S and C, and the same can be said for cos and secant. So just memorize that. And it's on your formula sheet anyway, so you should never forget. Now we can go ahead and we can use SOHCAHTOA. Let's write that at the top. And we can fill in the numbers that apply. So for sine theta, it compares opposite over hypotenuse. When I look at my triangle that I've drawn, my opposite side is opposite of theta. My hypotenuse is the longest side. It's also across from the 90. And the last side I label is adjacent. It's beside the angle, but not the hypotenuse. So now let me put these numbers in. Sine is O over H, so that's 4 over 5. Cosine is adjacent over hypotenuse, which is 3 over 5. And tan is opposite over adjacent, 4 over 3. A nice double check about trig ratios is that every number on your triangle should occur twice. So you should see 2 4s, 2 5s, and 2 3s. That's a good double check to make sure you didn't miss one or do one incorrectly. Now, if we've got the primary trig ratios, the companions are dead easy. We're just going to take the answer for sine and flip it. Same thing for secant. And same thing for cotangent. Dead simple. Now, this whole section here, I'm going to put a box around it because this is actually my answer to this question. Determine the 6 trigonometric ratios for the 0.34. There's 6 fractions that you need to write. And it's more than just the fractions that are important. I want you to count and make sure that when you're writing a trig ratio, you're writing 5 things. You're writing sine, cos, or tan. And now that we know companions, cosecant, secant, and cotangent, you're writing something for the angle. The angle is something we don't know. So you're calling it usually theta. You can call it x. You can call it alpha, beta. You can call it whatever you want for a variable, but you'll most often see theta. You put an equal sign. The angle and the equal sign are often forgotten by students. If you omit either of those or any part of this ratio, you haven't written a trig ratio at all. You've written maybe a floating fraction or part of an answer, and that really shows a very limited understanding of what's going on. So you need to make sure that you're always writing an angle with sine, cos, or tan. When we say just like sine equals, we've actually not said anything useful whatsoever. That's completely mathematically inaccurate. There's always an angle that goes along with a trigonometric symbol. Then you should have 2 parts to your fraction. And we do know that sometimes a denominator could be 1. So if you just see like a whole number or an integer, that's fine. There secretly is a 1 on the bottom. We just wouldn't write it. So count. That's 1, 2, 3, 4, 5 parts to your trig ratio. They all must be there in order to get the mark. Let's get a little more complicated now with a negative and some not so nice numbers. Determine the 6 trig ratios for the point -3,2 on the terminal arm of an angle in standard position. Make sure that you're reading these questions carefully. A lot of what's confusing about trig is that the questions are very wordy, but they really represent an easy thing. We're doing the exact same thing as before. There's really nothing that's 30-1 except for the companion trig ratios. Everything else you could have done in 20-1. It's just a matter of knowing what all of those little words mean, like the terminal arm and an angle in standard position. That all sounds very complicated, but all it really means is that you've got this line coming out of the origin on the Cartesian plane. That's all it means. So first of all, we need to draw this. The point -3, 2, I want you to think about what quadrant it would be in. Then draw your triangle and determine your hypotenuse. Try pausing the video and seeing if you can get the same picture as me. So I'm going to put this in quadrant 2, which means I really only need to draw quadrant 2. It's going to have a terminal arm coming out of the origin that has a point at -3, 2, point P. The way that I would plot that point is by going from the origin, -3 in the x direction and 2 in the y direction. Now, Pythagorean theorem is a squared plus b squared square rooted. These brackets are absolutely essential. When you square a negative, you should get a positive. If you don't put brackets in your calculator, you will get a negative, which will be wrong. 4 plus 9 is going to be 13. And there's nothing I can do to simplify square root 13. So that means we're working in this question with a hypotenuse that's a radical, which means we're going to need to do things like simplify a denominator with a radical, which is called rationalizing the denominator. We'll get there in a second. One note to make is that the hypotenuse is always positive. Okay, the only things that can be negative are the x and y coordinates that plot the point on the terminal arm. The hypotenuse is the distance away from the origin, and distances are measured in positive numbers. All right, let's set this up to state our answer. I'm going to write my primary trig ratios, and beside them, I'm going to write their companions that go with them. So I've got sine and cosecant, cosine and secant, and tangent and cotangent. Now I've used theta to represent the angle, so let's talk about where theta is on this picture. Theta is the acute angle in your triangle, but more precisely, I like to call this one my reference angle. So theta REF is what I use. The actual theta that we're representing in our trig ratios is the angle in standard position. What that means is the angle all the way back to the positive x-axis, that's right here, going counterclockwise until you hit the terminal arm. This green angle is theta. But we can't really do opposite over hypotenuse for a big obtuse angle like that. So what we know works is that if we do all the math with the reference angle, it is the same as that big green standard angle theta that you see. So let me put my numbers in here. I've got opposite, adjacent, and hypotenuse. Sine is opposite over hypotenuse. Let me fix that. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And then I'm just going to flip all of these for the companion trig ratios. Now, let's talk about a couple of these that, although correct, are not the preferred way to write the answer. This one and this one. What do you notice is different about these two than everything else? These have radicals in the denominator. We learned in grade 11 that we do not like radicals in the denominator. So we learned a method called rationalizing the denominator. I showed you this on the unit circle. Remember that it made all the denominators 2, which made memorizing the unit circle a lot easier. We actually prefer the denominator to have whole numbers in it instead of radicals. So for my first one, sine theta is 2 over square root 13. I don't like that square root in the bottom. The process that I need to do to rationalize the denominator is multiply by the radical that's in the bottom on top and bottom. Why does this work? Because anything divided by itself is equal to 1. And when I multiply something by 1, it doesn't change the value. So I'm going to get something that looks different, but is actually the same number. If you put the answer and the question in your calculator, you will get the same decimal. Now let me step back and tell you how I did that. When you multiply fractions, you go top times top. Multiplying radicals just means put the 2 in front of the root 13. You don't multiply those two numbers together because one is a whole number and one is in a radical. You can't combine them. On the bottom, I'm taking root 13 and I'm timesing by itself. Another way of thinking about that in math is if I take something and multiply by itself, I'm actually squaring it. Squaring and square rooting are opposites in math, and opposites cancel. That means I get whole number 13 in the bottom. As soon as the radical's gone in the bottom and it's a whole number, you've rationalized the denominator. The only other thing that happens sometimes is if you take a look at the two numbers, 2 and 13, that are not in a radical. Those are whole numbers, no square root sign around them. Those sometimes can simplify. If this was 2 and 14, you want to simplify that fraction down to 1 and 7. These, however, don't simplify, so 2 root 13 over 13 is the better answer. Let's try for cosine now, negative 3 over root 13. Some of you might end up doing this so many times that you can rationalize the denominator quite quickly because you'll notice a pattern popping up. You're still multiplying by the radical in the bottom, on top and bottom, top times top. Just write them beside each other, they can't combine. Bottom times bottom, the square root signs cancel, and you end up with 13. 3 and 13 cannot simplify any further, so you go ahead and write this as your final answer. Now every single one of our trigonometric ratios has a rationalized denominator, and we're done. One other thing to talk about that bothers some people is for this tan theta, see how there's a negative in the bottom? That sometimes will bother certain people. Some people have this rule that they think negatives should be in the top of a fraction. And yes, you will find that in some textbooks. But let's talk about negatives and fractions. For me, it doesn't matter where you see the negative. I'm fine with it anywhere, as long as you only see one. Because as soon as there's multiple negatives happening in a fraction, remember that two negatives make a positive. So you need to be really clear that your fraction is negative by either showing maybe a negative in the top like this, a negative in the bottom like this, or now this is one I don't prefer, a negative out in front of the whole fraction. I don't prefer that because if you have messy writing, your fraction line and your negative can sometimes look like the same line. And if you're not clearly communicating that it's negative, you're not getting the question right. So I actually prefer a negative in the top, but either of these is a-okay. As you can see from our answer, the tan theta had a negative in the bottom, and when I flipped it, cotangent had it in the top. Those are still the same answers if those negatives are anywhere else in the fraction. It doesn't matter where the negative is, as long as there's only one of them making the entire fraction negative. So if I was to put a box around my final answer, these 6 trig ratios, complete with the 5 parts, sine, cos, tan, theta, an equal sign, and 2 parts to the fraction, are perfect. Now you can see in this example that some of them are positive and some of them are negative. So let's just double check with our cast rule to make sure that this makes sense. Here's my cast rule telling me which primary trigonometric ratios are positive in which quadrant. We're working in quadrant 2. What does the S in cast tell you? That means that in quadrant 2, sine is positive, everything else is negative, but this is only telling you about primary trig ratios. So it's telling you sine positive means cos and tan are both negative. Now you can expand this. If sine is positive and cosecant is just the reciprocal of sine, then cosecant is also positive. Every other trig ratio should be negative. So take a look at your answer. Are sine and cosecant of theta the only positive fractions? Yep, looks like it to me. So we have done our job correctly. That's a quick double check at the end of the question to make sure you haven't dropped any negatives. All right. They're giving us a trigonometric ratio in this question. Cosine theta is 2 over 5 in quadrant 4. Determine the other 5 trigonometric ratios. Start with a picture, like always. I'm going to draw quadrant 4. I'm going to put my terminal arm in, and I'm going to connect a line back to the x-axis so I can see my triangle. Here's my reference angle. I've got a point on my terminal arm that I'm not actually told this time. That's okay. On this triangle, I have a hypotenuse, a side opposite of theta, and an adjacent. So let's take a look at what the question told me. Cosine theta is 2 over 5. The question has told me in a roundabout way that my adjacent and hypotenuse sides are known. Remember that cosine is adjacent over hypotenuse. By telling me this, they've told me my adjacent side is 2 and my hypotenuse side is 5. A little bit different than what we've been working with, but we still have Pythagorean theorem to figure out the opposite side. If we're given hypotenuse, however, remember Pythagorean theorem changes to be c squared minus b squared equals a squared. Send me an email if you need help with the rearranging of the Pythagorean theorem for that. 25 minus 4 is going to be 21. So now I know that on the picture I've drawn, my opposite side is root 21. But actually, that's only half correct. Think about how you would plot the point in quadrant 4. You would go in the x direction, positive, and then you would have to go down. So the root 21 is actually negative. Remember that I told you the hypotenuse was the part that was always positive. That says nothing about opposite and adjacent. Those can be positive, negative, or a combination of both. So that's something that you're just going to have to think through logically. The other way that you can catch it is if you write all of your answers with positive root 21 and then you check with the cast rule, you'll catch any negatives that you should have had. All right, they want us to determine the other 5 trigonometric ratios, which are sine. We already have cosine, but I like to write it anyway so that I can do secant easily, and tan. And then cosecant, secant, and cotangent. Let's start with what we know. Cosine is 2 over 5. That was given to us in the question, easy peasy. Secant is the reciprocal of that. Flip the fraction. Now I can look at my picture and I can do sine. Sine is opposite over hypotenuse, which is negative root 21 over 5. I'm going to flip that for cosecant. And I'd like you to pause the video and rationalize the denominator. The rationalized denominator for this question would be 5 root 21 over negative 21. Send me an email if you need help with those steps. They're spelled out on the last example, so rewind the video a bit and watch the rationalizing steps. Remember that that negative can be top or bottom, it doesn't matter. Tangent is opposite over adjacent. I'm going to do cotangent by flipping that, and I'm going to rationalize the denominator, and that will be my final answer. I'm going to double check that my signs all line up with where I am. I'm in quadrant 4. The only positive I should have is cosine and its companion, secant. Every other fraction has one negative in it, which is perfectly correct. That means they all have an overall negative sign. All right, giving you a little bit more information in this one in a different way. They're giving you cosine again, so this tells you that you have the adjacent and hypotenuse, and you can use Pythagorean theorem to find the opposite side. They've also told you tan theta is less than 0. What does less than 0 mean in plain old English? Less than 0 is negative. So if I think about my cast rule, they've told me cosine is 3 over 5, or if I dig into that number a little bit more, that's a positive number. Cosine is positive and tangent is negative. Which quadrant is that true in? Well, all signs are positive in quadrant 1, so it's not that quadrant. Sine is positive, meaning cosine and tangent are both negative. Well, our cosine is positive, so it's not this quadrant. Tan positive, definitely not that. Quadrant 4 is where we're working. All of this information in this first part here was given to you to tell you that therefore you're working in quadrant 4. So here I go with a sketch of quadrant 4. Let me put my angle reference angle theta in quadrant 4, I'm talking about cosine. So that's going to be adjacent over hypotenuse, 3 over 5. I'm going to quickly do Pythagorean theorem. C squared minus b squared is going to give me my opposite side. 25 minus 9 is going to give me 4. Or pardon me, 16, which I square root to get 4. Now, the way that I would plot this point, however, is go positive x direction and then down, which is the negative y direction. So that side of the triangle, I have to use logic to figure out that it's negative. Because from my Pythagorean theorem, my calculator is always going to give me a positive number. You have to actually use some logic to figure out that it's negative. Now, determine the reference angle and the angle in standard position. This is where reading is really important. Are they asking me to state all 6 trigonometric ratios? No, but some people would kind of be in the habit of that after all of these examples and just go ahead and do it. That's not necessary on this question. This question wants the reference angle and then the angle in standard position. The first thing to check is the mode on your calculator. We've learned about degrees and radians, and in Math 30-1, we work with both. That means you will constantly be switching between degree and radian mode on your calculator. If I look at a TI calculator right now, beside the blue button is a button that says mode. Right now, my calculator has degree highlighted. You can go down with your arrows, press enter, and you'll highlight radian. I'd like us to do this question in degrees, first of all. Then I can show you some radians in the next question. So I'm going to leave it on degree. If you ever want to get out of a screen on your calculator, you want to quit. So that's second mode. As you can see above the mode button, it says quit in blue. Now I'm back to my calculation screen. Let's review Math 10C. How do we find an angle on our calculator? Well, we have to do what's called the inverse trig ratio. So if my question told me cos theta is 3 over 5, and I want to solve for theta, I basically have to get rid of cosine. The way that I do that is with an inverse cosine. So on any calculator, if you find your cosine button, above it should be in a different color probably, cos with a little -1. That's the inverse of cos. The little -1 is what you press when you want to find an angle. So for most calculators, that's a matter of pressing second function cosine. Then you want to do the division that your question has. So 3 divided by 5. This is going to give me theta, or more specifically, reference theta. Let's look at what the buttons are on the calculator. Okay, I know where my cosine is, and I can see above my cosine button a cosine with a little -1 in blue. To access the blue writing, I press second cos. 3 divided by 5 is my cos ratio, and it's good practice to always close any brackets that are opened on your calculator. This is the answer in degrees because that's what mode I'm in. If I was in radian mode, it would give me a completely different answer. I'm just going to round this one to a whole number and say 53 degrees. So my reference angle is approximately 53 degrees. Remember, you have to put the degree symbol because putting no units at all really means radians. So that's part of the answer to the question. What is the reference angle? Now they'd like to know angle in standard position. To do this, you really need a very clear picture. I'm going to re-sketch what we have, but simplify it down a bit and show all 4 quadrants. So the terminal arm that I have for this question is in quadrant 4, and I actually know that this 53 degrees goes right there from the positive x-axis to the green terminal arm. However, an angle in standard position goes from the positive x-axis right there counterclockwise until you hit the terminal arm. Boom. I need to figure out how big the blue angle is. And I'm going to call this theta. It's fine to call one theta reference and one theta. How am I going to calculate that? Well, if you imagine the blue angle and the green angle added together, they would make a complete circle. A complete circle is 360 degrees. And if I take away the reference angle, all I'm going to be left with is the blue angle theta. So 360 minus 53 is 307 degrees. That is my angle in standard position. Another term that we can use is principal angle. Now let's review grade 11 trig and talk about the 4 possible calculations that you can do. So, depending on what quadrant we're in, finding our angle in standard position or our principal angle will be different calculations. If I'm in quadrant 1, the angle I'm looking for is exactly the same as the reference angle. Think about that. A terminal arm here, the principal angle always goes back to the positive x-axis. Well, in quadrant 1, so does the reference angle. They're the same thing. Let me try quadrant 2. Boom. To the nearest x-axis is my reference angle. From the terminal arm back to this positive x-axis is the theta I want. The calculation in quadrant 2 is to take half a circle, 180 degrees, and subtract the reference angle to give you the angle in standard position. Similarly, quadrant 3 is going to look like this. Reference angle, angle in standard position. So that angle in standard position is the reference angle plus half a circle. And as we saw in this question, the angle in quadrant 4 is a full circle, 360 degrees, minus the reference angle. One last example that has a different domain. So it's still very similar in what they're giving us to start with. They're giving us secant theta equal to 2 over root 3. That means that we've got 2 sides of the triangle, and we also have the quadrant or maybe quadrants that can be in because we know secant is positive. Now, they're telling us negative 2 pi to 2 pi is where we want to be working. This is called the domain. We're going to come back to this later. What I want you to do is I just want you to do the question as if we were just working within one full circle. That's what we did in grade 11. Then I'll show you how to work within more than one full circle, which is what the question is asking. So I've got secant equal to positive 2 over root 3. So if I think about my cast rule, secant is the companion to cosine. If secant is positive, cos is positive. Where is cosine positive? That isn't a trick question. It is positive in two quadrants. It's positive in the all quadrant and it's positive in the cosine quadrant. We actually are going to have a couple answers for this question, which is totally fine. Let's go ahead and draw those quadrants. Let's put a terminal arm in each quadrant. Let's draw the rest of the triangle in each quadrant. Let's put our reference angles in each quadrant. And let's figure out the sides. If secant is the reciprocal of cosine, and cosine is adjacent over hypotenuse, then secant is hypotenuse over adjacent. I'm going to put these numbers on my picture. Hypotenuse for each triangle will be 2. The adjacent side, which these two triangles actually share, is positive root 3. And then you can see that the opposite sides are going to be the same number, but different signs. In quadrant 1, to go in the y direction, I would go up, so positive. And in quadrant 4, I would go down. So I'm still going to do the same thing I've always done to find the opposite side, which is a squared minus b squared, or pardon me, c squared minus b squared. So I've got 4 minus square root and square cancel. 4 minus 3 is 1. The square root of 1 is 1. We already talked about this being positive and this being negative. And now we've got our picture drawn. We can start thinking about the reference angle. How would you calculate the reference angle? Well, we really didn't need this picture in order to calculate the reference angle. We really just needed this secant up here. Your calculators won't have secant on them. Some of the TI Inspires do, but when you write your exams, we actually disable that function. So you want to get used to always going back to the primary trigonometric ratios. Secant is cosine flipped. So to find my reference angle, I'm going to do inverse cosine on my calculator of root 3 divided by 2. Now let me make a note here that some calculators, depending on the version, will open a bracket under the root 3. You must close it before dividing. Some calculators leave your cursor under with the root 3, and it tells you must hit the over button to jump out of the radical before you divide. Make sure that you put this in your own specific calculator and that you're able to get the same answer as me. So I'm going to do inverse cos. So second cos square root 3. Now look at my calculator. A lot of you have this one. There is a cursor still clearly under a radical sign that has an arrow in it. If you don't want to be under the radical sign anymore, that's telling you to press this over arrow. Now you can see the cursor is no longer under the radical. Then you can divide by 2. That's very important. You need to know the difference between the division by 2 happening under the radical and happening outside of the radical, which is what we have in this case. That happens to be a really nice number. Could you have found that reference angle on the unit circle? Is root 3 over 2 on the unit circle for cosine? Absolutely. That's one of our points that we memorized. So if you remember that the first coordinate on the unit circle represents cosine and it's root 3 over 2, you could figure out that it was 30 degrees without using your calculator at all. Reference angle is 30 degrees. Now, you might ask yourself why I'm doing this in degrees when the domain above has pi's in it, so it wants us in radians. We're still learning about degrees and radians, so it's fine to do things in degrees first to understand the trig, And then you can start to get to the point once you've practiced where you try and do this stuff in radians to start with, in which case you might be doing a reference angle of pi over 6 instead. Now we're in quadrant 1 and 4. Okay, so this is 30 degrees. This is 30 degrees. The angle in standard position for something in quadrant 1 is the angle, the reference angle. So 30 degrees is one of our answers because we're in quadrant 1. Sometimes it isn't one of our answers if we're not in quadrant 1. The angle down in quadrant 4 is this whole angle here, which is a full circle minus the reference angle. So 360 minus 30 is 330 degrees. This is half of the answer. Let me show you what domain this is working from. We worked from the positive x-axis, and we said all of the answers in one full circle. What that is in terms of a domain is it's all the answers from the 0 line to one full circle, 360 degrees. Okay, if I did this in radians, it'd be all the answers from 0 to 2 pi. Now, if you look back at our domain for our question, we've gone to 2 pi, so we've got half the answers, but now we need to go to negative 2 pi. We have to do a negative circle. So our positive circle went counterclockwise, so our negative circle is actually going to start at the 0 line and go backwards. That's going to be negative 2 pi to 0. So let's draw this again. This is really complicated. We've got two terminal arms with 30-degree reference angles. We are now going to do a domain of negative 2 pi to 0. What that means is we're starting on the positive x-axis, and instead of rotating in the positive direction, we're going to rotate in the negative direction. So one of our answers is that big black angle that I just drew. The other answer is this smaller black angle. I just rotate in the opposite direction until I hit the terminal arm. So since I rotated the opposite way, that's an arrowhead since it's not really nicely drawn. Since I rotated the opposite direction, my answer for that one is going to be negative 30 degrees. It's still 30 degrees size-wise. It just happens to be clockwise instead of counterclockwise. If I think about the bigger black angle here, again, that's an arrowhead. That big black angle has rotated almost a full circle, but it's 30 degrees short, and it's also in the opposite direction. So if I put these answers together, I have two answers in the positive direction and two answers in the negative direction. So my answers for theta for this question are negative 330, negative 30, 30, and 330. However, write this, highlight this, make this big. If the question starts in radians, you must answer it in radians. So all of this work is great, but we're not quite done until we change every single answer up there into radians. So my final answer for this, and I really only have to change 2 because whether it's negative 30 or positive 30, it's the same fraction. I'm starting in degrees and I want to go to radians. So that means I'm multiplying by pi on the top and 180 degrees on the bottom so that the degree units cancel. I'm going to put 30 divided by 180 in my calculator and I get 1/6 and I just pop the pi on. Review lesson 1 if you don't remember how to do this. I'm doing the same thing with 330. I'm going to divide 330 and 180 on my calculator and I get 11/6 and I just pop the pi on the top. So my answers therefore are negative 11 pi by 6, negative pi by 6, positive pi by 6, and positive 11 pi by 6. So that is the full solution to this last question. Page 201 has some textbook questions that you can practice with. And as well, I'm assigning assignment 4.1 to 4.3 for extra practice. It's on the website. The key is also posted on the website. Do the best you can and check the key periodically. Make sure that you can reproduce the unit circle without looking at anything. Using your calculator is fine to check decimals. Make sure you ask for help if you need it. And this week is all about practicing to make sure some of these basic skills are mastered before we move on to solving trig equations. Again, if you have any questions whatsoever, don't hesitate to send me an email.